For this section, we're going to be introducing the basic concepts of trigonometry that will then develop as we go into the more complicated problems that we come across. So the first thing, the most basic thing in trigonometry is the definition of an angle. And an angle is formed by two rays or line segments meeting at a common point, which we call the vertex. So, I have two examples drawn here. The first one, we have two line segments, line segment AC and line segment AB, intersecting at the point A. So in this case, A is the vertex, and the angle CAB or BAC is formed from these two different line segments intersecting. The same thing is true for the rays AC and the ray AB. So a ray basically looks like a line segment that just continues off in one direction. It doesn't go in both, that would just be a standard line. So these two rays are intersecting at the point A, and we have the ray AB and the ray AC create the angle CAB or BAC with a vertex of A. When you're putting notation for these angles, you'll notice how I kept saying CAB or BAC. I didn't say, for instance, ACB. That would be a different angle. You always start with the top left or the top right and then work your way around. So again, this could be written as the angle CAB or the angle BAC. If we wrote this as the angle BCA, then that would mean we're talking about the following angle in red. BCA would mean we're talking about this angle here, which really doesn't even exist because we don't have line segments or rays noting that angle. So it's very important to keep track of these letters when you're going through it. Okay, from here, to measure an angle, we say that we begin with the initial side and rotate about the vertex, so that point of intersection, to reach the terminal side. Rotating counterclockwise gives a positive measure, and rotating clockwise gives a negative measure. Typically, when we talk about angles, we're going to be using the coordinate plane as a reference, and when you use the coordinate plane as a reference, the positive x-axis, meaning if we were to draw out a coordinate plane, then this part of the x-axis right here is your initial side. Okay, but in these examples, sometimes the initial side will be noted. It won't be this value here, it'll be stated where the initial side is. So to measure the angle, you always start with this initial side, and you rotate counterclockwise until you reach the terminal side, which would mean this value in green is the angle. But you need to make sure that you are starting with the initial side. Looking at this first example, it's pretty obvious that that's what the angle would be, but the second example, the angle is a bit different than you would think. Starting at our initial side and rotating counterclockwise, we end up getting this value in green is the angle. So whereas in the first example the angle was maybe something like 40 degrees, in this second example the angle is maybe closer to 300 degrees. Even though it looks like the angle would be this value, that would be rotating clockwise, which we do not do. We rotate counterclockwise. If we rotated clockwise, then we would be giving a negative angle. Okay, so continuing on from here, we now note the definition of a degree. So in this section, we'll be talking about the 3 ways that we could classify an angle. So the first way that we'll talk about is the degree, which we say is 1/360th of a complete rotation. And then if we create a second definition about a complete rotation, the second type of angle that we'll talk about, a complete rotation is 360 degrees. So it goes both ways. A degree represents 1/360th of a circle, and a complete rotation represents 360 degrees. So if we want to convert 45 degrees to rotations, then that means we're going to take 45 and we're going to multiply it by our conversion for the degree symbol, which we said is 1/360th of a complete rotation. So we'll put that here. Okay, so now we just have to multiply this out. To multiply 45 and 1/360th, we're going to put 45 over 1. And then from here, we're going to cross cancel. So we have 45 on the top, 360 in the denominator. Each of these is divisible by 5. So if we divide 45 by 5, we'll be left with 9. If we divide 360 by 5, 5 goes into 36 7 times. There'll be a 1 left over, which leaves us with a 10. And 5 goes into 10 2 times. You could always use a calculator to check that if you have trouble dividing. That's perfectly fine. And then from here, 9 and 72 have a common divisor of 9. So we can divide the top and bottom by 9, leaving us with 1 over here and 8 over here. So 45 degrees is the same thing as 1/8 of a rotation. So typically in this course, the 2 ways we'll define angles are degrees and radians, and we'll talk about radians coming up. But it's worth discussing what these values mean in terms of rotations, because rotations are how we visibly see an angle. A degree may be intuitive in some cases, but when you try to picture 237 degrees, it's not extremely easy to picture where that is. Whereas if you try to picture 2/5 of a complete rotation, it is a bit easier to put that into perspective. You could draw a circle, divide it into 5 equal parts, and highlight 2 of them, and that would give you an idea of what that complete 2/5 of that complete rotation looks like. So these problems that we're doing right now are just to give us an idea of how to picture what 45 degrees would look like. From here, we now want to convert 1/3 of a rotation to degrees. I want you to take a moment, pause the video, see if you can't find this conversion on your own. Okay, so trying this together, 1/3 of a rotation. If we take this 1/3 of a rotation, and we convert it, then that means we need to multiply it by its conversion factor. 1/3 of a rotation, we know that 1 rotation is equal to 360 degrees. It's perfectly okay if you didn't write it out like this when you did your work. I'm just showing exactly what's going on here. If you just took 1/3 and multiplied it by 360 degrees, you're still doing the right process here. But this rotation will now cancel out with this rotation, meaning we are just left with degrees as our units. And now we have 1/3 times 360 degrees over 1. We can cancel a factor of 3 from the numerator and denominator, leaving us with 1 in the denominator and 120 in the numerator. So we are left with 120 degrees. So 1/3 of a rotation is the same thing as 120 degrees. All right, so continuing on from here, we'll say that for our next definition, an angle theta. So whenever we talk about angles in trigonometry, typically we refer to them with Greek letters. It's just so that we don't mix up the value of a length, for example, with the value of an angle. This is not required. It's perfectly fine to say the angle x. It just makes it cleaner looking when you're going through your work. So typically you will see theta, this symbol here, referenced, and things like alpha, which is this symbol right here, whenever you're talking about an angle. And just to be clear, if it's not perfectly visible what's going on here, theta is basically the capital O with a line in the middle of it. You can also see it referenced with a squiggly line in the middle of it, and sometimes you'll also see it referenced with a line that has these two little sides on it. Any of these is perfectly fine to demonstrate that you're dealing with the angle theta. So, going back to this definition, an angle theta is called acute if theta is greater than 0 degrees and less than 90 degrees. From there, it's called a right angle if theta is exactly equal to 90 degrees. And finally, it is called obtuse if theta is greater than 90 degrees but less than 180 degrees. This less than 180 degrees isn't commonly known, but it makes more sense when we start talking about reference angles later on. Essentially, when you deal with an angle like 370 degrees, you would want to call it obtuse because it's greater than 90 degrees, but when you actually find its reference angle, that might not be the case. So, just always keep this in mind, an obtuse angle should be less than 180 degrees. Alright, from there, we introduce our definition that says two angles are coterminal if one is equal to an integer multiple of 360 degrees plus the other. So, I want to make sure I'm explaining this order of operations correctly. We take some integer, so meaning any whole number you can think of that's positive or negative, and we multiply it by 360 degrees, and whatever that result is, we add it to the other angle, and if we get the angle that we started with, then the two angles are coterminal. This might not seem very important, but this is actually going to be very critical, this coterminal term, as we go through trigonometry, because it is very useful when we start wanting to reduce angles down to only the critical information we need from them. So, with this process, before we try some examples on this, we'll introduce the process for how this works. We say if you're given two angles and you want to determine if they are coterminal, we'll call the first angle theta and the second angle alpha. It doesn't matter which one you pick, just label each one of them theta or alpha. And when you do this, you are going to set 360x plus theta equal to alpha. And when you do this, you will now solve for x. Because when you solve for x, if x is an integer, remember a whole number that's positive or negative, then theta and alpha are coterminal. And if x is not an integer, then they are not coterminal. So, let's see if we can't try that out. We want to check our 110 degrees and 830 degrees coterminal. So we'll start by taking 360x plus one of our angles. It doesn't matter which one. I'm just going to pick the smaller one. Equal to the other angle. And now we'll solve for x. So we're going to subtract 110 degrees from each side, which leaves us with 360x equals 720 degrees. And then dividing each side by 360, we're left with x equals 2. Technically 2 degrees, but the degree symbol doesn't matter in this case. All we care about is this a whole number that's positive or negative? Meaning, is it an integer? And in this case, it is. So that tells us, yes, 110 degrees and 830 degrees are coterminal angles. Coterminal, just to be clear on this, means if you were to look at a graph, so if you were to look at this angle plotted out, so 110 degrees would look something like this, if we were to actually draw it. Then if you were to take this angle and do a complete rotation around, and then another complete rotation around, 830 degrees would be where you'd land after 2 complete rotations. Meaning, if you're coterminal, if 2 angles are coterminal, then they share the terminal side of the angle. So both 830 degrees and 810 degrees fall on this terminal side. So hopefully now you can see why this method is so useful. 830 degrees and 110 degrees end up having the same terminal side. So if we wanted to do some work with this, with these angles later on in the course, and we had 830 degrees to deal with, then essentially we could just use 110 degrees, and all of our calculations should theoretically work out the same way. While that's not always true, we can't just say 830 degrees equals 110 degrees, because clearly they don't. They are different angles. They have different numbers, that is to say. But when we use them in most of our calculations, they will end up representing the same exact thing. Okay, so from here we now have 240 degrees and 1,500 degrees. We want to decide if they're coterminal, and feel free to use a calculator on this problem, just to save yourself some time. Go ahead and pause the video and try this out. Okay, so trying this together, we have 360x. If you really cared about that degree symbol being left in your answer, you could always put a 360 degrees times x, but it's good either way. Plus, we'll pick 240 degrees equals 1,500 degrees. We'll subtract 240 degrees to start getting our x alone. And when we do that, we get 360x equals 1260 degrees. And now if we divide each side by 360, we'll be left with x equals, and like I said, you can use a calculator on this one really quickly. 1260 divided by 360 gives us 3.5. Is this an integer? No, it is not. So are these two angles coterminal? No, they are not coterminal. Remember, if these were sentence problems, we would want to give a sentence answer. But in this case, these are just sort of written out. They're not much of a sentence problem, so you can just put yes or no for these. Okay, continuing on, we can now introduce the reference angles that I was talking about a little while ago. So a reference angle, which we'll call theta, is one that lies in quadrant 1 and is found by taking the terminal side of theta and finding the angle that meets the x-axis. So, in other words, if we take an angle in quadrant 1, to be in quadrant 1, that means to be in this corner of the coordinate plane. So this is quadrant 1, this is quadrant 2, quadrant 3, and quadrant 4. Remember, we always rotate counterclockwise. So we start 1, then go to 2, then 3, then 4. So reference angles should always end up in quadrant 1 unless otherwise specified, which means they always need to be between 0 degrees and 90 degrees. They can equal those values since these are the quadrantal angles. Quadrantal angles are this, 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 and this. So, as long as the value is greater than or equal to 0 or less than or equal to 90, it is a reference angle. And we find it by taking whatever angle we're dealing with. So for instance, in this one, we have the following angle. Remember, we always start at the positive x-axis and rotate counterclockwise to our terminal side. So this is the angle that we're dealing with. To find the reference angle, we would take our terminal side and connect it to the x-axis, the closest x-axis. Never connect it to the y-axis. That's a very common mistake. You cannot do that. But in this case, we connect it to the x-axis and we get the following angle. This angle is the reference angle for this large angle. But it's not always easy to picture what this angle is. In fact, if you look at this example, what angle are we dealing with? Even I don't know. I would have to get out like a protractor to measure this, and even then it wouldn't be very accurate. So instead we have this graph here. This graph says if your angle is in quadrant 1, then you have your reference angle theta. If it's in quadrant 2, then you take whatever angle you have and subtract it from 180 degrees. That will give you the reference angle. If it's in quadrant 3, take your angle and subtract 180 degrees from it. And if it's in quadrant 4, subtract that angle from 360 degrees. If the angle is larger than 360 degrees, then you need to add or subtract 360 degrees from it to get rid of those extra complete rotations. So if it's a negative angle, you'll add 360. If it's a positive angle, you'll subtract 360. And that will get you inside of these 4 quadrants between 0 and 360. And it has to be less than 360, just to make sure that's clear. 360 degrees lies on top of 0 degrees, so you would need to subtract 360 from it. And from here, you could then use one of these four formulas to find the reference angle. If your angle lies on these quadrantal angles, so on the x or y axis, then you can use either formula. So for instance, if your angle is right here, well, let's use this one. If your angle is right here, so this is 270 degrees, this is 180, just to make a note. If we needed to find the reference angle for 270 degrees, we could take 270 and subtract 180 from it. That would give us 90. That's in quadrant 1. Or we could take 360 and subtract 270, which would again give us 90, which is in quadrant 1. So either one is perfectly fine. All right, so let's go ahead and try these two examples. We want to find the reference angle for 540 degrees. So starting off, notice this is greater than or equal to 360 degrees, so we have to start by subtracting 360 degrees from this value to get rid of that extra complete rotation, which we can't have when we're finding a reference angle. So 540 minus 360, we can just do some quick mental math here. If this were 560 minus 360, we'd have 200. Subtract 20 from that, and we have 180 degrees. Or you could just use the borrow method. If we borrow 1 from our 5, we get 4. Bring the 1 over. 0 minus 0 is 0. 14 minus 6 is 8. 4 minus 3 is 1. All right, so now that we have 180 degrees, we have to check, is this between 0 and 90? It is not, so we need our reference angle. So, which formula do we need to use for 180 degrees? Well, 180 degrees is right here. It's one of our quadrantal angles. So we can use either formula it's connected to, 180 minus theta or theta minus 180. It'll give us the same result either way. So if we just use 180 degrees minus theta, so minus 180 degrees, we'll be left with 0 degrees. So 0 degrees is the reference angle for 540 degrees. All right, from here, I want you to take a moment, pause the video, see if you can't find the reference angle for 830 degrees. Okay, so trying this together, 830 degrees, we clearly have some extra rotations going on here. And as it turns out, we have 2 extra complete rotations going on. So we're going to subtract 360 2 times, or we could just subtract 720 degrees. When we do this, 0 minus 0 is 0, 3 minus 2 is 1, 8 minus 7 is 1, so we get 110 degrees. We check, is this value between 0 and 90? It's not, so we have to use one of our formulas. In this case, 110 degrees is between 90 and 180. If we were to draw it out, it would look something like this. So since we're in quadrant 2, we use our formula 180 minus theta. So we have 180 degrees minus 110 degrees, which leaves us with 70 degrees. 70 degrees is the reference angle for 830 degrees.